Hi, this class we will learn about MOSFET and we'll talk about the MOSFET equation. And there are two region. First is the linear region, and the second is the saturation region. And third, and finally, we will talk about the ID-VD curve and the ID-VG curve. First, let's talk about what is MOSFET. MOSFET is a simple word of metal oxide semiconductor and field effect transistor. So we can say this part MOSFET. So the metal oxide semiconductor, we had learned about the MOS last class. So the MOS is the structure of this device. So the structure should be metal oxide and the semiconductor. And the FET are the scheme of the how this device works. So it is effect, field effect transistor. So what is transistor? So transistor is the word word that are the combination of trans and the resistor. So the transistor is like some kind of that changes the resistor so that controls the current, how much current are flowing. So but this transistor use the field effect. So let's have an example of the MOSFET. So this is the MOS structure. So the top part is the metal, and the lowest part will be semiconductor, and between the metal and the semiconductor should be oxide part. So we say this part gate and this part body. And we will use first P-type semiconductor on the semiconductor part. So we will say this part P sub. And let's have some example on it. So in MOSFET, we have some N plus poly on it here. This part will be source and the drain, and but we'll talk later. First, we'll talk about the gate bias on it. So let's think about when we have some plus bias on the gate side. So we will talk this part V sub G, and this will be positive. So when there are the positive on the gate bias and the body on the minus bias, so you will have a vertical electric field on it, and the direction will be top to bottom like this. And then, but the electrons direction will be the opposite to the electric field than we had learned in the electrodynamics. So when you cannot understand why the electrons direction is opposite to electric field, you should learn electrodynamics again. And the electrons will be here, and it will be accumulated on the surface part because the electrons can go over to the silicon dioxide because the silicon dioxide are the dielectric things, so it can go over to the silicon dioxide, and we will get increase the gate bias in the positive side, and electrons will get accumulated, and when there are strong inversion on it, we this part or like it will act like N-type semiconductor. It actually that part was P-type semiconductor, but there's our electrons get accumulated, and that part will not should be the P-type semiconductor, and that part, the surface part will should be the N-type semiconductor. So the energy band diagram sings about the strong inversion we had learned at last class. So that will be the sufficient condition of the strong inversion will should be the pi s is 2 phi b, and that when that condition there will be the strong inversion, and we say the channel had be struck channel had be start. Yes, there will be some channel on it, and we say there are n plus, and there are connected now. But don't be confused because that there are not current flowing because we don't had learned about the source and drain. So first, we talked about the vertical electric field, and the vertical electric field makes the channel on it. And we can say that we can next say about the source and drain. Source and drain are the we use the polysilicon on it, and there are some terminal on it, and we can use the bias on it. So the source is the we we are injecting the carrier on it. So when we use N plus poly, and then we injecting the electrons, and that part will be the source. And when we use P plus silicon on it, polysilicon on it, and when we injecting the hole to the part, and that part will be the source part. So and then the when we injecting the source, and it goes through the channel, and that goes out to the drain. So first of all, when we use N plus polysilicon on it, the majority carrier will be the electrons, and the electron when we use this part source and this part drain, the electrons will get goes left to right. So the direction will be the right side. But the electron's direction and the current direction will be the opposite. So the current flows to drain to source in N plus polysilicon. So we say this channel are made by electrons, and we can say this part N channel. And when we use P plus polysilicon on the source and drain, uh, the channel will be made by the hole, and we say that part that the channel are P channel. So let's say this part are P plus, and these are the source. So the holes goes left to right like this. So the holes are getting the right side, and the holes direction and the current direction are same. So the current flows to source to drain. So the N channel and the P channels of the current direction will be the opposite. So this was the channel and the source and the talking about the source and drain. But let's have some example of the let's have some example like there are some like this lake and there are some well on it and there are having some water on it. But in this case, there the water can can flow to source to on other side, but and like this water wells are on the left and the right side, and but when we have some gradient on it, and I will have some the right well goes goes go low go low, and the water will flow to the left to the right. So in this picture, the water will go through this part and the waters are flowing. This is the MOSFET. So so this is the source and this is the drain. And when we have minus bias in the energy band diagram, the energy band diagrams go up, but this is so, but we have the plus bias on the energy band diagram. The energy band diagram go to goes lower then. So if we have some drain on the plus bias and the source on the minus bias, the drain will goes to the bottom. So and then there will be some current flow. But this was some kind of um non-expert expert talking, but we are now in majoring in electro electronics engineering. So when we have some drain on the plus a drain on the bias plus bias on the drain side and the minus bias on the source side. So electric field will have some drain to source like this. So it will be the right to the left and the and plus poly majority carrier are the electrons and the electrons direction will be the opposite to the electric field and electric the electrons will go through like this to the source to the drain. So and then there will be some current flowing. So there are two conditions to having some current flowing. So the VG. So we say we in MOSFET. So MOSFET is actually four terminal devices. So the gate and source and drain and the body. So there will be have four terminal on it, but it is too complex. So we use the source side and the body side, and we connect the source and the body side. So and then we have some ground on it. So actually, MOSFET we use like some terminal device. So when we have some grounding on it, so source and the body will be 0 volt, and we just control the gate bias and the drain bias. So in gate bias, we had learned about the strong inversion, the sufficient condition to have a channel. So the gate bias should be bigger than the threshold voltage. So the threshold voltage we had learned last class, and the threshold voltage we can get this value on the flat band voltage plus pi aux plus pi s, so the pi surface part. So and that will be the threshold voltage, and the gate bias will be bigger than the threshold voltage, and then the channel will be uh, on the piece of the surface part, and then we have to do the drain voltage on positive side, and these two are the criteria for the to flow of to current flowing. So this is was the simple talking about the MOSFET. So actually, it when we have some the gate bias are bigger than the threshold voltage, and there will be some channel on it, and drains are getting bigger and bigger and bigger, and the waters will be bigger and bigger. And but we there are like some this will be the M plus, and this is the channel. But when there are too strong bias on the drain side, and there are very strong electric field on this channel, the channel will change like this. The drain side channel will be get thinner. And then when there are too many bias on the drain side, the channel will change like this. And this part are like some kind of we are like pinching like this. So we say this part this condition pinch off. And then when the pinch off are offered, so started, so the current are n- getting the current goes through like this, and on this part the E field get the electrons goes here. So and then the current getting have a constant value on it. So we can say this part are the saturation region, because it doesn't getting increasing it doesn't increase, and it is like it moves like uh, it doesn't get higher when we have some additional drain bias on it. Actually, it is not constant, but we can say it is constant value. And this part we actually said it current flowing like this. The before the pinch off had offered, we said that the linear region. Why this part or the linear region? We can say this part we can say this I can say this by drawing the IDVD curve. So this is the IDVD curve, but you have to remember that the gate bias should be bigger than the threshold voltage, because when the threshold of the gate bias if the gate bias are smaller than the threshold voltage, there should not be some channel on the surface part. So when in this condition, the when I ever increase the VD, it doesn't the any current are not flowing because so you should remember that in the ID-VD curve, we have to say the gate bias are bigger than the threshold voltage. So in this condition, the when we increase the drain bias, the the current are increasing. But when the pinch off are offered, the current are getting the constant value, so it move like this. But like when we have some bigger gate bias on the gate side, the channel thickness will be getting bigger. So the current can goes flowing well. So I can draw again more this, this, this. So we can say VG and VG and VG. This will be the ID VD curve, and this part, this part will be the edge of the saturation region, and this will be the saturation, and this part will be the linear region. So in the linear region, the ID will be the W over L. The W will be the width of the MOS structure, and the L will be the channel length, and mu C ox, and the mu will be the mobility of the carrier, and the C ox will be the capacitance of the oxide, and Vg minus Vt H and Vd over 2 and Vd. And we can say W over L mu C ox and Vg minus Vth and Vd and minus Vd square over 2. But when the Vd are very lower, it have a very small value on it, we can negable on this part. So we can finally say W over L mu C ox and Vg minus Vth Vd. And this will be the formula of the linear region current and the saturation current. The Vg minus Vth or the V, it is equal to Vd. So in the saturation current, mu C ox and the Vg minus Vth are equal to the Vd, and that will be the edge of the saturation region. So Vd minus Vd and Vd. So it will be, this part will be Vd over 2, and so W over 2L and mu C ox and Vg minus Vt square, because the Vg minus Vt is equal to Vd. So I say just like this. So this will be the saturation region current. So This will be the IDVD curve. And next, we will talk about the IDVG curve. IDVG. So when we increase the VG, there are any current flowing, but if the gate bias are bigger than the threshold voltage, and there will be some channel on it, and then there are have a sufficient condition for the current flowing. So in this ID-VG curve, we have to say VD are having some value on it, because if the VD are zero, if there are no non-bias on the source drain side, it it have just a channel, and there should not be some current on it. So we have to say in this curve, VD are bigger than zero, so the VD have some positive value on it. So there are none of current flowing, but when it is the gate bias are bigger than the threshold voltage, the current get goes increase on it. So these are the ID-VG curve. So it was the ID-VD curve, and you should remember these two formula on it. So this was the NMOS MOSFET. So we use the N plus poly silicon on it on the source and drain, and we use the N channel. So we say this are the NMOS. And when we use on the P plus polysilicon on the source and drain, and we will make the P channel. So we can say this part are the PMOS. So, but you should not confuse that when we use P sub, it is NMOS, and when we use N sub, and it is PMOS. But these are the wrong thing, because the NMOS and the PMOS are decided by the polarity of the channel. So, but we have I can say we can say about one example when we use P sub, but we use the accumulation region before we talked about the last class. So there will be some P channel. So it is PMOS. Actually, we use P sub. So these are the wrong knowledge about it. So you should decide it. This is NMOS and PMOS by the channel polarity of the MOSFET. So thank you for watching my video, and next class we will talk about the CV characteristic of the MOSFET and some kind of parasitic capacitance on it, and then we'll talk about the CMOS, the most important devices on the modern semiconductor field. So thank you for watching my video, and then yep.